Okay, so we are going to talk about finding limits graphically. And so this is our first topic of Calculus 1. Welcome to the class. First thing before I talk about how to describe this and what is a limit, let's get some notation down. So if I ask you to find the limit of a function, you're going to see this notation. The limit, LIM, as x approaches c of f of x equals L. And so that what this means is if f of x becomes arbitrarily close to a single number, which is L, so that's what it's coming close to, as x approaches the value c, so the c here is an x value, and this L is a height, so that's a y value, from both sides, then the limit as x limit of f of x as h approaches c is L. That is, a limit is the y value, or the value a function approaches, not necessarily what the value of the function is, but the value of what the function approaches from both the left and the right sides of a given x value. So here are two examples. So here in example A, we're going to look at this function. First, I want to figure out what is the function value at -3. So at -3, here's the dot on the graph, it has a height of 4, so our function value is 4. Then I'm going to ask you, okay, so now let's find the limit as x approaches -3 of f of x. So we go to the left of -3, which here is like a -4, and then see what we're approaching as we get closer and closer to this -3 value on the x-axis. And that seems to be approaching a height of 4. And then likewise from the right-hand side, it also seems to be below a height of 4, but getting closer and closer to the height of 4 as I go from -2 up to -3 and on the axis. So that means my y values are approaching a height of 4. So therefore my limit as x approaches -3 of f of x is also 4. Now, the only difference between this graph A and graph B is we have an open circle here at -3. So the function value, f of -3, is undefined. There is no function value there. It does not exist in this. But the limit as x approaches -3 from the left-hand side is getting closer and closer to 4, and from the right-hand side, it also is getting closer and closer to 4. So the limit as x approaches -3 of f of x is 4. So the function value and the limit does not have to be the exact same thing. We're just saying what is the pattern of the graph approaching from the left and the right as it gets arbitrarily close to this x value, in this case -3. Now there are a number of cases in which the limit does not exist. We're going to focus on 3 in this semester. You'll learn a few more as you go up in higher level calculus classes. But for our course, the f of x approaches a different value, a different number from the left side of c as it approaches from the right side of c. So if it approaches different values from the left and the right, do 3 examples here, and this one of these is going to have multiple examples. All right, so if I'm approaching, let's say this is my function here, and this we'll call this f of x, and then this value here is going to be my value c. Okay, and so as you can see, if I'm approaching from the left of c, I'm getting closer and closer to this height up here, this positive height. So I'm approaching from the right of c and getting closer and closer to c. I'm way down here as a y value. So my height from the left and my height from the right is different. So I'd say the limit as x approaches c of this function does not exist. And so we abbreviate that DNE. Now, our second case is if f of x increases or decreases without bounds as x approaches c. So think about asymptotes. Okay, so what this would look like graphically is, let's say, okay, here's our c value, and then we're going, let's say we have a function that's going like this, and then a function that's going like this, as we're getting closer and closer to this c value. And this is c. Okay, so as I'm going to the left of c, it's approaching infinity. As I'm going to the right of c, it's approaching negative infinity. So it's decreasing on that right-hand side without bounds, and on the left-hand side, it's increasing without bounds. And so, therefore, we can say the limit, we'll call this g of x. The limit as x approaches c of g of x does not exist. Now, I do want to say one caveat for this type of example here, that way that it goes to bounds, is there are some cases that we will be a little bit more exact than D and E. For example, let's say we have this rational function. All right, it's approaching that asymptote here. All right, and so if I was looking at, okay, what's happening to this graph as x approaches this c value? Well, from the left, it's approaching infinity. From the right of c, it's also approaching infinity. So it's growing without bounds, so technically the limit does not exist. But notice that it's growing without bounds in the same direction. The left is going to infinity, the right is also going to infinity. So we write this a little bit different. We tell the reader how the limit does not exist. So we would say the limit, we'll call this h of x. The limit as x approaches c of h of x is equal to infinity. Okay, infinity we cannot reach, so it's not a constant, so the limit does not exist, but you're giving the reader more information. You're telling them how it does not exist. They're both going from the left of c and the right of c. I know my graph is both going up to infinity. All right, the last type of way that the limit does not exist that we will focus on is if f of x oscillates between two fixed values as x approaches c. So let me show you what this would look like on a graph. So here again, this is our c value. So if we have a function that goes like this and then just kind of bounces back and forth, and it might go back up or it might tailor off, but in this, around this interval of c here, it's bouncing back and forth at a fixed height. Okay, let me change my color. So we're bouncing out between this height, this positive height here, and I'm bouncing between this negative height. So it's bouncing up and down, up and down, up and down in between that height. And so we can't decide, is it the positive value or the negative value is approaching, because it's getting really, really close, really, really fast. I can't draw it as close as it actually gets. So we would say the limit, we'll call this j of x. The limit as x approaches c of j of x does not exist, because it's bouncing between two fixed values. So make sure you can recognize those three cases where the limit does not exist. All right, so let's do a few here. Here's a graph of function f of x. And we're going to ask you to find a few limits. And I'm just going to walk through it. Now, before I do this, you'll notice down here, if you look at course A, B, and C, we have some different notations. They almost look the exact same question repeated over, except on the first one, we have the limit as x approaches some value with a little minus sign up here of the function. Now, what that little minus sign means is that we only care about what's happening from the left-hand side of that x value c. So this is called a left-hand limit. And so we're only looking at the one side. And if it has a little plus sign, you probably figured that out, that is only looking at the right-hand side. What's happening from the right of that c value. So if I ask you to find the limit as x approaches -2 from the left of f of x. So here's my f of x, there's -2. So from the left, that's smaller than -2 going toward -2. So I'm looking at this value. And I see that my graph is approaching positive infinity. And that's all you have to do that left-hand limit there. Now B, for this right-hand limit, the limit as x approaches -2 positive from the right-hand side of f of x. So we look from f of x from the right-hand side, it's also going to infinity. So the limit as x approaches -2, well, this one, because it doesn't have a plus or a minus, that means it has to be both sides, the left-hand side and the right-hand side. So the left-hand side is going to infinity, right-hand side is going to infinity, so the limit is also going to infinity. Then, what is the function value? This one's saying, what is the actual function value at -2? Well, there's an asymptote there. So this is undefined at that point. Our function does not exist at that point, it's undefined. All right, let's move on then to the limit as x approaches 1 from the left of f of x. So here is x value of 1 from the left of 1. We're getting closer and closer to a height of 2, so we'd say that limit is equal to 2. The limit as x approaches 1 from the positive side of f of x, that would be up here. We're getting closer and closer to a height of 4, so that limit is 4. And the limit as x approaches 1 of f of x, well, the left is approaching approaching 2, from the right is approaching 4. They are not the same value, they're different values. That's that first exception that we had, so the limit does not exist. And then the function value, what is actually function value? Well, from the left, when it's approaching 2, notice that's an open circle, so that's not the function value. We would have to move down here where we have that dot filled in, so that would be a function value of -1. All right, the limit as x approaches 3 of f of x, so limit as x approaches 3 of f of x is in here. So notice this graph is jumping back and forth really, really quickly in between a height of 2.5 and a height of 4.5. So that's that last type that does not exist. It's oscillating between two fixed values. So this would be D and E. Okay. Now if we're asked to find, that's too light. If we're asked to find the limit as x approaches 6 from the left of f of x for j, from the left of f of x is approaching a height of 4. The limit as x approaches 6 from the right of f of x, that's approaching also a height of 4. So the left-hand limit is 4, the right-hand limit is 4, so the limit as x approaches 6 of f of x must also be 4. But what is the function value at 4? Well, that's this dot here. The function value is actually 2. So limits and function values are not necessarily the same thing. Now that we know how to look at a limit graphically and figure it out, we're going to start learning some algebraic notation for limits. Now, before we can do that, we got to do some notations. So first thing you want to look at is for this following section, we're going to C and K are just some real number, some number, and N is a positive integer. So the limit as x approaches a number, C, of K, another number. Well, think about that. Our function is a number, like f of x equals 2 or y equals 2. And the graph of y equals 2 is a horizontal line. So regardless of where we're on that horizontal line, we're always going to be approaching that same height of 2, or height of k. So the limit as x approaches c of k is k. And the limit as x approaches c of x, well, x, that means our function value is y equals x. So if x value is c, that means our y value has to also be c. So our answer is just c. Now, limit as x approaches c of some number times a function, well, that's equal to, we can factor out that number, that constant, and that becomes that constant times the limit as x approaches c of f of x. So we can figure out what that limit value is and then times it by that constant c. So we factor out the constant. We can do a similar thing if we have a function raised to a power, and so that becomes the limit as x goes to c of f of x, and that answer raised to the power. Okay, moving to the second column here, if we have the limit as x approaches c of f of x plus or minus g of x, so this is the sum or difference of limits, that's the same as the limit as x approaches c of our f of x function, plus if we're doing sum, minus if I'm doing difference of the limit as x approaches c of g of x. So we just kind of like think about it as if you're distributing that limit notation to each function. And we'll do the same thing here if we're multiplying two functions together. So this becomes the limit as x approaches c of f of x times by the limit as x approaches c of g of x. And then likewise, if I'm doing the limit as x approaches c of a quotient, f of x divided by g of x, that is equal to the limit as x approaches c of f of x, whatever that value is, divided by the limit as x approaches c of g of x. Okay. And then the limit as x approaches c of x to the n, well, we're going to put these two properties here together, and that becomes the limit as x approaches c of x, and we take that answer raised to n. Well, by our first star there, the limit as x approaches c of x we know to be c, so that has to be c to the n. Now, this last one, this is a composite function. So when you have a function inside of a function, how do we determine the limit? Well, in order to find the limit of a composite function, you first have to know you first need to find the limit of the inside function. Because notice my composite function here is f of g of x, and g of x is my inside function. So if I know the limit as x approaches c of my inside function is equal to L, then I can say the limit as x approaches c of f of g of x is equal to the limit as x approaches. Well, my inside function approaches L, so that means now for my outside function, I need to be approaching L. So the limit as x approaches L of the outside function. So this is the outside function when you're looking at that function notation. So this is the only one where the value here changes of your limit. So this started at the limit as x approaches c, but now we're actually going to figure out the limit as x approaches L. And L is our answer that we got when we found the limit of the inside function. All right. Let's apply this. So I've given you the limit as x approaches 2 of f of x equals 9. Limit as x approaches 2 of g of x is -4. And limit as x approaches 2 of h of x equals 3. That's all you know. You don't know what this graph looks like. Now I've asked you to find this a and b. So let's look through this first example. We're going to find the limit as x approaches 2 of 3 times g of x minus f of x. So first thing I want to do is I have this difference, so I can distribute that limit notation. To each function, and that becomes the limit as x goes to 2 of 3 times g of x minus limit as x goes to 2 of f of x. Then I know 3 here is a constant, so I can bring that out. And that becomes 3 times the limit as x goes to 2 of g of x. That answer minus the limit as x goes to 2 of f of x. Now I know that from our given information, the limit as x goes to 2 of g of x is -4. And the limit as x goes to 2 of f of x is 9. So that gives us -12 minus 9, which is -21. So we found the limit of this function. All right. So let's say now we're going to find the limit as x goes to 2 of this problem in b. So I notice I have a plus sign here, adding these two fractions. So let's start with that same property, that a sum property, and it's going to be the limit as x goes to 2 of the first fraction plus the limit as x goes to 2 of the second fraction. Then we have our quotient rule. If I'm taking the limit of a fraction, that is the same as the limit as x goes to 2 of the top, the numerator, divided by the limit as x goes to 2 of the denominator function. And I'm going to do the same thing on the second fraction here. And that's the limit as x goes to 2. That's kind of big. Let me go a little smaller. The limit as x goes to 2 of the top function divided by the limit as x goes to 2 from the bottom function. That's using our quotient rule there. Now, to do our next one, notice that the cube root, recall that you know that the cube root of x is equal to x to the 1/3. So this is like saying x raised to power. And so we're going to use that power rule, but I'm going to keep it in the radical form. So that means I can bring that power out. So this becomes the cube root of the limit as x goes to 2 of -16 times g of x over the limit as x goes to 2 of h of x plus the limit as x goes to 2 of 3 times h of x over the limit as x goes to 2 of 2 times f of x. So that's using that power rule. Okay, next I notice I have a constant inside this limit, -16, so I can bring that constant out. Now it's going to stay inside the radical, but it's going to come out of the limit notation. And then this second denominator stays the same. And then for the second fraction, I have a constant of 3 in the numerator and a constant of 2 in the denominator. So those constants can come out of the limit notation. Okay. And now we have the limit as x goes to 2 of f of x, limit as x goes to 2 of h of x, and limit of x goes to 2 of f of x. And that was in our given information. So Whoops, that's in our given information. So if we look back here, the limit as x goes to 2 of f of x is 9. So we got the cube root of negative 16 times some value over some value plus 3 times the value, 2 times the value. Well, the limit as x goes to 2 of f of x was 9. So I can plug in a 9 there. Okay, and the limit as x goes to g of x goes to 2 of g of x was negative 4. So in place of g of x, we can plug in negative 4. And then the limit as x goes to 2 of h of x was given as 3. So I'm going to plug in 3 here and 3 here. Okay. And now it's just doing some math here. So the cube root of, well, negative 16 times negative 4, that becomes positive, divided by 3 plus 9 over 2/9, so 2 times 9, so that's 1/2. And then finding a common denominator, that'll give us 11/6. That's what that simplifies down. Okay. All right, last thing we're going to look at is we're going to do this. We're going to use these properties here. Now this was algebraically. Now what if I didn't give you the algebra of the function, but I just gave you the graphs of the function so you can figure out the values. So I didn't give you what the values equal at certain points, but I gave you the graphs so that you can combine what we learned about graphing limits graphically with what we just learned about limits properties. So that's kind of what we're going to do in this example 4. Notice the first graph is the entire f of x function, this piecewise function here, and the second graph is our g of x. So I'm asked in A to find the limit as x approaches negative 2 of 2 times f of x plus 3 times the quantity, the g of x squared. So first I'm just going to use my properties here and work through this. And so this is the limit as x goes to negative 2 of 2 times f of x plus the limit as x goes to negative 2 of 3 times g of x quantity squared. So that's using my sum property. And I'm going to take this constant out. So that's 2 times the limit as x goes to negative 2 of f of x plus 3 times the limit as x goes to negative 2 of g of x quantity squared. Then I'm going to use my power rule. And that becomes 2 times the limit as x goes to negative 2 of f of x. That term stays the same. And then the limit as x goes to negative 2 of g of x quantity squared is the same as the limit as x goes to negative 2 of g of x, and that answer squared. And so now I want to figure out the limit as x approaches negative 2 of f of x is. So I look up here at my f of x graph, find negative 2, and I see from the left it's approaching a height of 1. From the right it's also approaching a height of 1. So I can say the limit as x approaches negative 2 of f of x is 1. Okay. Now I need to figure out the limit as x approaches negative 2 of g of x is. So I go to my g of x function, and I see from the left of negative 2, we're approaching a height of 2. From the right of negative 2, we're also approaching a height of 2. So therefore we can say the limit as x approaches negative 2 of g of x is 2. And so now I got 2 times 1, which is 2, plus 4 times 3, which is 12. 2 plus 12 gives us a 14. So there is our limit that works out. All right, now let's look at this composite function. We want to find the limit as x approaches 1 of f of g of x. So remember, to do the composite function, we first need to find the limit of the inside function. Okay. So that means I need to figure out what the limit as x approaches 1 of g of x equals. So I'm going to look at my graph, my g of x graph. Let me take this off. Okay, so my g of x graph as x approaches 1. So from the left, we're approaching a height of 2. From the right, we're approaching a height of 2. So that meant our function value here is 2. So to find the limit as x approaches 1 of the composite f of g of x, that's going to now be, I need to figure out the limit as x approaches, and I use this value here, 2, of the outside function. So now I'm going to switch my g of x function, and it's the x equals 2 that I'm looking at. And so from the left is approaching a height of 2. From the right, it's also a height of 2. So my answer is 2. Now, it just happened to be that our answer from the inside function and answer in the outside function is the same. That will not always happen. Don't expect that. So since this occurs, then we can say this occurs. So that's my final answer. Okay, so that is the introduction to limits graphically. And we'll go and practice this next class, our first class. Have a good day.